into the how part of the composites, which is essentially getting you into the structural analysis per se. And though we'll be, as I said, discussing from composite point of view, its special case will be valid for metals, at least until the point of failure. And when we have to do metals, we don't need to do this particular thing, on which I'll not focus too much. We'll spend just the first few minutes of today's class. Is micromechanics. As I said, something similar to this is done in the case of metals as well, but it's mostly by material scientists at the crystal level, and to develop newer materials like single crystal metals or metallic alloys for typically high temperature applications in aircraft engines, etc. There are single crystal nickel alloys which are much more capable for that particular application than most of the other known metals or alloys. But from a composites point of view, this is almost like an essential. We have to do this before we get on to macromechanics or analyzing the structural component as a whole, which means that we'll have to spend a little bit of time, at least the very basic models which are used to do this. So what is this all about? Micromechanics, as the name suggests, it's essentially at the micron level, which is essentially at the fiber diameter level. That's the kind of length scales that we are looking at. And this is a whole subject area by itself. There can be at least a couple of courses which can be taught purely on micromechanics itself, and we'll focus on the simplest of those models, which is kind of intuitive as well. It's essentially coming from like how you calculate the density of a mixture, for example. You know, if there are two materials in a mixture and they have different densities, then you just multiply the density by volume, add it up so that you get the total mass, and then you take the fractions of each one of those elements mass, and then you end up with the volume fractions, and you can use that for various things. So the same thing is utilized in the case of composites as well, to get some of the properties, in particular the moduli along the desired directions, right? So the rule of mixtures is what we call it, because the fiber and the matrix, the two components of the composite, form essentially a mixture, and we use that the rule typical of mixtures in order to arrive at some kind of an averaged out quantity. So when we talk of composites, we will not be having a single Young's modulus E. We will have a Young's modulus which is along the fiber direction, perpendicular to the fiber direction, and any other quantities also, like for example the shear moduli will have to be either along L and T, that is longitudinal and transverse, or it has to be TT, which is both transverse direction, etc. So we start having the requirement to have subscripts for the Young's moduli. So for example, E subscript L refers to the modulus of the composite along the longitudinal direction. But longitudinal, we mean a direction which is parallel to the fibers in that particular layer. Other layers might have fibers in a different direction, but in that particular layer, whatever direction the fibers are, whatever is the Young's modulus of the composite, which is fiber and matrix put together, is what we are looking at. So obviously it's going to have contributions from both the components. One is the matrix, the other is the fiber. So starting with the contribution from the fiber, it is the longitudinal modulus of the fiber, which is what we are writing as E subscript L. F. L stands for longitudinal again, just like on the left hand side, and F stands for the fiber. So, and then there is a VF, which refers to the volume fraction of the fiber. What fraction of the overall volume is the that of the fiber. So in case idealistically we assume there are no additives, the volume fraction of the fiber plus the volume fraction of the matrix should be equal to 1, because if you are having half of matrix and half of fiber, the VF and VM will both be equal to half each, and the total will be 1. But typically, since we'll have a few additives, VF plus VM in most practical cases would be slightly less than 1, about 0.9 to 0.95 or so, depending upon what, how many and how much of additives you are adding. And the second term, of course, is involving the Young's modulus of the matrix. So it's very clear to see that there is contribution both from the fiber and the matrix, but usually EM is so low compared to ELF that the contribution from the second term is kind of negligible. So this will be contributing almost 90% or more of the overall modulus of the composite in the longitudinal direction. But the same is not true in other directions. Okay, so now this is something that is very easy to kind of prove. So typically what you do is you say that essentially there are two materials involved over here. So one is the fiber, which we are denoting as small f, and the other is the matrix, which we are denoting as M. And suppose we were to apply a certain force field over here, or a stress field in tension, and we are trying to pull it across. The reason why F and M are in this is because this is longitudinal modulus that we are interested in, and therefore we have to apply the load parallel to the fiber direction, length of the fiber, and we want to measure the stress and the strain that is happening over here. Now it's very clear that I can integrate the stresses over the fiber, and this particular portion, if I call it as the load PF, and this particular portion what the matrix is taking as PM, it's quite clear that the total load P that this can take is PF plus PM. On the other hand, since they are assumed to be perfectly bonded to each other, in other words, the load that we are applying is small enough so that this joint between the fiber and the matrix doesn't give up. In reality, of course, the cross section of this would look something like this. Essentially there's the fiber over here and the matrix all around, but we are just kind of lumping together this whole thing so that we are instead looking at the cross section, which is something like this, right? So it doesn't matter for us because only the overall area is of concern to us. So that's why we are lumping all of this fiber together and lumping all of the matrix together, and we are looking at it from that point of view. Okay, so now it's clear that this is essentially the load that you have, and then you also can see that the if these are perfectly bonded as we said, then both of them are going to be extending by the same amount. So in other words, if there's a change in length delta L because of this extension load, then that delta L that you're going to have is going to be in the fiber as well as the matrix, right? So your delta, so if you're going to write the strain in the 1-1 direction, so if you're introducing, let's say, a coordinate system that is having x1 along the length of the fiber, x2 and x3 are perpendicular to the direction of the fiber. Now the gamma that we are interested in is gamma 11, alternately written as gamma LL to refer to the longitudinal direction. So you can either write it as 11 or LL, it is equivalent to each other. So this particular gamma 11 in the composite, that is C, is equal to the gamma 11, that is the strain in the longitudinal strain in the fiber, is also equal to the longitudinal strain in the composite, matrix, right? Now why? Because the strain, normal strain, is defined approximately as the change in length divided by the original length, and you see that whether it is the original length L or the changed length delta L, they are the same for both the fiber and the matrix. And what we are trying to get into, because of this whole derivation process or procedure, is to have, instead of two separate materials F and M here, I want to have the same area that you see over there, but I would like to have a uniform material in this entire thing, which I call as the composite C. So this is a fictitious material, this is not real. That is what is real, where you have the fiber and matrix separately with a distinct interface between them. But for all mathematical purposes, all the derivations, etc., it's good to have, instead of separate properties dealing with fiber properties, matrix properties and their volume fractions, you want to have a unified set of properties for the composite as a whole, right? Now let's go back to the first equation. P is equal to Pf plus Pm, and we can write these forces as the stress times the area, right? So now let's say the area of this is AF and the area of cross section of this is AM. So which is essentially at the cross sectional level. I'm talking about this as AF, this area, and this is essentially your AM. In reality, of course, AF will be equal to pi d squared by L for this area, and this would be, if let's say it's L by B, so you're essentially talking of a LB minus pi d squared. So if this is the diameter, let us say d, so then your the space which is occupied by the fiber is pi d squared by 4, right? Because pi r squared is the area of the cross sectional area of a circle, so it's pi d squared by 4, and your overall area is LB, that is of the composite as a whole. So this will be the actual volume fraction. So I'm just dividing that into two rectangular portions over here, and that's what I'm considering along the length over here. So this is the x1, x2 view, and this is essentially your x2, x3 view, right? So you're actually seeing it at the cross-sectional level when you cut how it is. This is the reality of x2, x3. This is how it actually is. But without loss of generality, we can do the same by assuming this. For this particular exercise, it doesn't matter whether you consider it this way or this way. So we are just doing this for convenience. Okay. So now when we do that, first of all, the load P is equal to the stress in this particular area, and we'll assume the same stress in the entire fiber. So that is essentially your sigma F, and this is sigma M is the stress in the matrix. So stress multiplied, normal stress multiplied by the cross-sectional area of that particular element is going to give the total load that that particular element is taking. So in other words, I can replace for the composite, P is equal to the stress in the composite, that is sigma C, which is also along the same direction, 1, 1. Let me follow the same convention, 1, 1 C. So times the total area, right? Now here the PF can be replaced as sigma 1, 1 of the fiber times the area of the fiber in the cross-sectional level, right? Similarly, this can be written as sigma 1, 1 along the matrix, and that multiplied by the area of the matrix, right? So the total force that is applied on the composite is partly taken by the fiber and partly taken by the matrix, and the sum is what we are looking at over here. Now we can divide this whole equation by A. When we do that, we will get sigma 1, 1 of the is equal to sigma 1, 1 in the fiber into AF divided by A, plus similarly you will have sigma 1, 1 in the matrix area of the matrix divided by the total cross-sectional area, right? Now if you multiply this by the length L that we were talking about over here, multiply and divide by L, it doesn't matter, right? So when you multiply and divide each term by L and L, it doesn't matter. So now AF times L is nothing but the volume of the fiber, right? So this is the volume of the fiber, and this is the total volume. Similarly, this is the volume of the matrix, and this is the total volume, right? So when you have this, you very easily see that the total stress in the composite is volume fraction of the fiber times the stress in the fiber plus the volume fraction of the matrix times the stress in the matrix, right? So now that is very clear. So now we can write the stress using Hooke's law that you would probably be familiar from the deformable bodies course for this simple case as just the Young's modulus times the strain in each one of them. So in other words, I can write sigma 1, 1 in the as the composite in, of course, because all of this load and strain measurements are all happening in the x1 direction. So that's why it is L or 1, 1 either way. So this ELC multiplied by the strain, which is your gamma 11 or gamma LL equivalently, right? So now that is the strain in the composite, right? Now similarly, I can write your sigma 11F, the stress in the fiber, as the Young's modulus of the fiber times the strain in the fiber. So in other words, I put your sigma 11F as the Young's modulus of the fiber, again of course in the longitudinal direction, multiplied by the strain in the fiber, right? And same thing I do with the matrix as well over here. I put it as the Young's modulus of the matrix, which is usually isotropic, and therefore I don't need to say EL unless you have some very rare special cases where the matrix is also anisotropic, and therefore you'll have to specify the direction. So here it is just EM, and then I have to multiply it by the stress in the matrix, which is what with the strain in the matrix, which is your gamma 11M, right? Now I've already said that gamma 11C is equal to gamma 11F is equal to gamma 11M, because it's all of these are equal in turn to your delta L divided by L, right? So it's they are all extending by the same amount because of the perfect bond that is there between the fiber and the matrix. And whether it is the composite that we are talking about extending by a delta L, or the fiber separately or the matrix separately, they're all original length is L and the new length is L plus delta L, and therefore all of their strains are the same. So I can cancel out the gammas in this particular equation, whether it is gamma 11C here or gamma 11F here or gamma 11M here, and then I finally end up with this particular equation where EL is equal to ELF VF plus EM VM. Okay, so there are certain things that you need to remember in terms of the assumptions we used in order to arrive at that. One is the fact that these are perfectly bonded to each other and therefore they are having the same strain, otherwise this would not have kind of worked. And also that we are assuming only fiber and matrix to be present, there are no additives. But it's very simple to see that if I have just one particular additive, let me call it A, then I would just have another term over here, EA VA, which is the volume fraction of that additive times the Young's modulus of the additive. So it would not be too difficult, but the problem is that usually the additives are spread out in a different way than the fiber and the matrix, so the additive may not extend through this entire length, and so it's not like I can actually use it that particular way. It might not be continuous along the length, it might be at certain locations along length depending upon how you're kind of mixing it, etc. So it's not as simple as that, but something that can be handled as long as you know the geometry of what is happening. So now this is a very simple situation where you're applying the load along the fiber direction, and therefore you're able to get the Young's modulus of the composite along the fiber direction, which we call as the longitudinal modulus EL, as the function of the longitudinal modulus of the fiber and that of the matrix, which is isotropic, and therefore I'm not putting L explicitly over here as a subscript, and it's essentially a weighted average of these two, and the weighting function being the volume fractions of those two individual components. Is this clear? Any doubts or questions? Yeah, Nilesh.
What does the LL stand for?
Come again?
LL?
LL? Okay, a good question. So where specifically are you asking for that?
Say for like gamma, strain.
Yeah, okay. Yeah, so remember that the strain is a second order tensor. So just like a scalar is a zeroth order tensor and a vector is a first order tensor, in the sense that one direction is required for a vector and two directions are required for a strain, right? So typically when we say we have two subscripts, gamma ij, I refers to the cross section on which this is acting, and j is direction in which it is acting, right? So 1 it refers to fiber direction, because fiber direction is longitudinal direction, that is along the length is something that in English we call as longitudinal. So it's just that instead of writing 1 1 in each one, I'm repeating, and so I'm calling it as. So this could be as, this is a repeating. Whenever the indices are repeating, either it is 1 1 or 2 2 or 3 3 or LL TT, etc. Essentially it's a normal strain, right? Because it's essentially an elongation if it's positive and a contraction if it is negative, right? Now on the other hand, if this were 1 2, I would be putting this as LT. So L corresponding to the direction of the fiber and T corresponding to any cross-sectional direction which is perpendicular to the fiber, right? And that is essentially what this LL stands for. Many a times you might drop that if it's a repeat. Sometimes you might just call it gamma 1 or gamma L. Just like actually, truly speaking, this EL should have been ELLLL. Actually, 4 subscripts would have been needed because the E, remember, is a 4th order tensor because it relates the stress to the strain. So when it relates stress to the strain, stress is a 2nd order tensor, strain is a 2nd order tensor. So the coefficient that are going to be there will have 4 subscripts. So if you want, let's say sigma ij as a function of gamma kl, then what needs to multiply gamma kl to get to sigma ij is cijkl. Okay, so in other words, it's a 4th order tensor, and you strictly speaking should have probably written this as ELLLL, right? So, but it's understood, and we use this compact notation to refer to the longitudinal modulus, because what it actually refers to is the relationship between capital gamma 11 and sigma 11. So I'm applying in a particular component, let's say the fibers are all running through this, which means that is the one direction as well as the longitudinal direction, equivalent ways of saying the same thing. And then I'm trying to pull this, so the force is applied on the x1 plane. So in other words, x1 axis is perpendicular to that cross section. So I'm applying force which is in the x1 direction. So therefore the stress is 1 1. And similarly, the strain, if I put a strain gauge over here and try to measure that, so I'm essentially measuring a normal strain which is gamma 11. So it's a relationship between a sigma 11 and a gamma 11. So therefore that particular material coefficient is C1111. The first 11 refers to the stress, the second 11 refers to the strain. So that's essentially what it is. Okay, so sometimes you might see the LL, sometimes you might just see an L, so it's kind of understood. So but strictly speaking, it has to be double L because 2 subscripts are required for all 2nd order tensors. Just like for vectors, when you put a vector components, you say V1 or V2, V3, you take the measure numbers along IJK, 3 unit vectors, right? So you say VI, VJ, VK, you can put it as. So essentially you need only 1 subscript over there for a vector, but for a 2nd order tensor like a stress or a strain, you need 2 subscripts, and that's essentially what we're talking about. Right? Any other questions? Anybody else? Okay, so that's as far as EL is concerned. So the homework that you will have is just like how we derived for this. I would like you to derive for something else, which is the Poisson's ratio. So the Poisson's ratio is, remember, when you are applying a stress in one direction and measuring the strain in a perpendicular direction. So for example, you are in this case, you typically, whenever this is a convention for Poisson's ratios, so we will always have 2 subscripts when you are dealing with composites. So when you have LT, for example, the first subscript always refers to input, the second subscript refers to the output. So the input is the stress, whatever stress you are applying, and the output is the strain that you are measuring. And Poisson's effect is always a correlation between normal quantities, that is normal stress with normal strain, okay, but just that they are in orthogonal directions. The applied stress is in the longitudinal direction and the measured strain is in the transverse direction, okay. not that the longitudinal stress will not cause any longitudinal strain. In fact, that is the main result, and which is what we saw over there, but it will also cause a contraction in the other direction. This is something that you would have probably been aware of anyway, that when you try to pull this, it's not only going to extend in one direction, but it's going to contract in the cross-sectional direction always, and that is essentially when you have a positive Poisson's ratio. But it is possible that even in isotropic materials, you can have negative Poisson's ratios. There are certain negative Poisson's ratio materials where when you're trying to pull it in this way, of course it extends that way, but it can also extend in these two directions. So there are certain materials like that. For example, cork, which you typically use to close bottles, that cork material is essentially with a negative Poisson's ratio, and that is why you use in that particular application, because it seals much better than any other material. Okay, so the reason why these things work like that are essentially in terms of the geometry that they have, in terms of the microstructure, how they are within. So there are many different kinds of materials which can have such negative Poisson's ratios, but one example of a microstructure which can do that is what is known as an inverted M. So for example, if you have M and a W, let's say, which are putting one below the other, an M and a W. So now you can see that if this is the x1 direction and this is the x2 direction. Okay, now we're not talking of composites, we're talking of even an isotropic material where the internal geometry is something like this, and then when you're trying to apply a load like this, which is essentially a stress, then you can see that when I'm trying to stretch this, what happens in the other direction, these V's that are there and inverted V that are there in the M and the W tend to go out. In other words, when I'm pulling this, you typically expect most materials to contract in the other direction. In fact, in incompressible materials, that would be the maximum contraction that you would get, typically like rubber, for example, whose volume remains the same. So because your length is increasing, your cross-sectional area will decrease, so that the overall volume remains the same. That is one extreme of kind of material. The other extreme kind of material that you have is where you can have negative Poisson's ratio and go all the way up to -1. So typically isotropic materials, of which metals are an example, you can prove that your Poisson's ratio is between -1 to +12, right? So this is essentially incompressible materials like rubber, and anything in fact which is between 0 and -1, any negative values, these are all called typically as auxetic materials. And they are finding a lot of renewed interest in aerospace engineering, because many different kinds of geometries are being developed with these kinds of materials. Just like this is just an example. This is not true for all the negative Poisson's ratio materials. They could have many different other geometries also, which when stretched in one direction will stretch in the orthogonal direction as well. So this is just a very simple to illustrate geometry that I'm showcasing over here, but typically you would have the same kind of an effect coming from a few other geometries as well. So what I want you to prove as the first part of today's homework, remember that the next class is on Wednesday, that is day after tomorrow, so I wouldn't want you to rush it into Wednesday's class. So whatever homeworks I'm listing out today, you can probably present to me next Monday. So you'll have a full week to work them out. Okay. So just like we started off with the fiber properties and the matrix properties here and got to composite property, here also we are starting with the fiber property, which is the Poisson's ratio LT, which means I'm applying a load in the L direction, the stress is sigma LL, and the strain that is resulting is gamma TT. So it's the relationship between them, and the Poisson's ratio, remember, always is defined as the ratio of the strains in the transverse to the, write it down. So you probably are aware of this already, but your nu LT is defined as gamma TT by gamma LL with a negative sign in the definition, so that when it is when the Poisson's ratio is positive, then they will have opposite signs. That when tension, there is one tension in the other direction, there is compression in the other, in terms of an effect in terms of strains, right? So this is the case when you are applying only sigma LL is non-zero, all other stresses for all I comma j not equal to LL, right? So that's your definition of a nu LT. Always remember that the first subscript is an input and the second subscript is an output. That is the convention. In terms of the order of the subscripts. The first subscript is what occurs first, that is your input. The second subscript is what occurs later, which is the output, right? So for this nu LT, there is a nu LT for the fiber, there is a nu LT for the matrix, but the matrix is isotropic, so you don't need an LT subscript over there. The nu is the same in for any two orthogonal directions. That's why you see that this is written just as nu M, right? So be careful with these two might look very similar, but this is nu M, which is Poisson's ratio, and this is Vm, which is the volume fraction of the matrix. Okay. So whereas in the what we proved in the class, we had to apply a load in one direction, measure the strain also in the same direction. The only thing you're going to do different is you're going to apply a load in the same way that we did for the what we worked out in class, but instead you're going to measure the strain in the other direction. Okay, so what adds up and what doesn't, it might be slightly different in that particular case, because for example, when we are trying to pull it apart this way, both the fiber and the matrix was stretching by the same amount, whereas when you're trying to pull it in a perpendicular direction, the total stretch will be the sum of the stretches of the fiber and the matrix, right? Because they are next to each other, so that change is going to be there, and which is why you will see certain differences. But there will also be differences associated with which direction you are putting, and therefore there will be a slight recombination that will be happening, and eventually you will get to this, which looks very similar to this in terms of the how the fractions are enabling it. So this is a fairly straightforward, simple extension of what we did. The next thing that we will have is in terms of the transverse direction, where things get a little more complicated. But if you are familiar with let's say in electrical theory, you would have inductors and capacitances, or for example you have in springs and dashpots, when you have them in series and or parallel, you know how they get kind of added up. Okay, in one case they get added up like this, that as if they are the sum. In the other case they get added up as if the reciprocals are summed. Okay, so when their reciprocals are summed, we can of course get the inverse of that reciprocal, and it looks a little more complicated than that, but essentially this is saying that your 1 by Et of that is of the composite is equal to Vf by the Et for the fiber, and Vm divided by the Em for the matrix. So that's essentially what you are trying to use those fractions in order to evaluate your Et, and so this is your transverse modulus, right? So your 4.2, the homework will be to kind of derive your GLT. So ET is something that we will not look at. It's very similar to GLT. So if you're able to do one of them, you can do the other one. So just like we did one of these pair in the class and the other is a homework, here you just take this for granted and you derive just the Young's the shear moduli. Okay, now shear moduli, just like Poisson's ratio, will involve two quantities, but here that order doesn't matter. So GLT and GTL are one and the same, because essentially the shear modulus is a change in the right angle. So because when you're applying a shear to a particular area, so then what is happening is that an initial right angle is going to change by a certain amount, and it's that change that which is measured by your shearing strain, and what is the resistance that the material offers to that is what we call as the shear modulus in the in that particular plane. So this is essentially your LT plane, which means that the plane involves a longitudinal direction, it involves a transverse direction. So if all the fibers are running along this, along the length of this particular thing, then the L direction is parallel to that, and T is anything that is perpendicular. So LT can be like this, or LT can be like this, or LT can be like this. Any of these are all called as LT, right? So that is your LT direction. And so whether it is LT or TL doesn't matter, because it's the 90 degrees between L and T that I want to see the change what is happening. Whether I say the angle between L and T or between T and L, it is one and the same. So it's essentially a change in that angle between two directions. So therefore, unlike in a Poisson's ratio where the order is very important, in other words, nu LT can have entirely different numerical value from nu TL, okay? Whereas here GLT and GTL are by definition equal to each other. They are one and the same, right? So once again, it's the matrix is isotropic, so there's only one shear modulus associated with the matrix, and therefore GM doesn't have any additional subscript of LT over here. It's just GM as it is, okay? And then you have the other quantities which are kind of self-explanatory. Are there any questions or doubts about these two homeworks? Yeah, Manish.
So over like the volume fraction, like how to find that, or like
Yeah, good question. So typically what is done is you do what is known as a burn test. So you make the material, you take a specimen out of it, and then you burn it so that you get different kinds of ashes, essentially for the polymer and then the fiber. So before you burn it, you weigh the whole thing, and then after you burn it, whatever remains, which is the fiber, you tend to weigh that, and then you can also know the densities of these two materials. Based on that, you work back to get the volumes. So then you know the volumes of the original volume of overall composite, and then how much of fiber volume is left, and therefore the difference between them, the volume of the matrix, and therefore the ratios give you the volume fractions. So that is one way of doing it. There could be many other ways of doing it as well. Yeah.
So that's something that we can find.
Yeah. Another way is if you can probably within a specimen count the number of fibers that you have in a fairly small cross section. Each fiber is, let's say, a circular diameter, so each has a cross sectional area pi d squared. So let's just like what I think we drew over there, a rectangle with a circle in between, which is a cylinder. So essentially the cross section of a cylinder is pi d squared multiplied by the number of fibers within that area divided by the overall cross sectional area is another way of getting the volume fraction. Anybody else? Any questions? Okay. So most important, as is the case with all homeworks hereafter, will be to state the assumptions at each point of invocation. So I don't want all the assumptions put together at the up front, because you don't know which assumption is used where, and even if whether some assumptions are even utilized or not, it might just be there without even being utilized, in which case that assumption is not even necessary, right? So state each assumption wherever it is being utilized, that means the point of its invocation, and then comment on its validity also. Just like what we were doing in the case of trying to get EL, we said that one of the assumptions was that the fiber and the matrix were perfectly bonded to each other. Okay, without that, we could not say that gamma 11 for the composite equal to gamma 11 for the fiber equal to gamma 11 for the matrix. That was possible to say if and only if you had the perfect bonding. But how valid is it in reality? Well, it is valid as long as the loads and strains are of a reasonably small value, because once you go beyond a certain value, then there is a possibility of the shearing stresses between the two being so large that they can debond at certain locations, if not all. Okay, eventually it could be all as well. So that is something that I want you to kind of state while you do the derivations. Don't just blindly go step after step. Just say when you're going from step 1 to step 2, what is essentially being assumed and how valid is it in reality. Okay, now this is beyond the scope of this course, but just I wanted to give you a flavor of what is actually used in the industry and also academia and also research papers and things like that. So there are certain other corrections that you need to do in order to be able to utilize those formula, simplistic formula that we derived, mainly because the assumptions there are kind of too idealistic, right? So it's good for a first cut analysis, especially for preliminary design, etc. Those will give you reasonably good ballpark values, but not something that is trustworthy for more advanced modeling, especially detailed design, or let's say damage dynamics and trying to understand the mechanics of how the damage grows, etc. In all those kinds of places you will need more refined models. And two examples of those refined models is what I am bringing out. There are numerous examples in the literature. One is Halpensai, the other is Brintrup, and they bring in quite different corrections to that, whatever we were talking about over there. One is in terms of the heterogeneity, because there's so much of mismatch in the stiffnesses of the fiber and the matrix. Fiber is extremely stiff, the matrix is very flexible, relatively speaking. So therefore there needs to be certain correction. Other correction is because of the fact that your length is much larger compared to the diameter of the fiber, and that specific geometry, which is what was so advantageous as we saw in the previous class, that can create certain complications as far as the mathematical modeling, and therefore the micromechanics relations that we derived can depend on L by D. They can depend on the heterogeneity and the L by D. So how does it depend? For example, if you're looking at the transverse modulus, which we said was just following that reciprocal law, it was fairly simple, but in reality it will have a few corrections which are involved with L by D and beta, where this beta, for example, is a measure of the heterogeneity. For example, if the materials that you are using for both the fiber and the matrix had the same Young's moduli, then you would see that ETF minus EM will go to 0. So therefore your beta will go to 0, and therefore the second term will go to 0 in the numerator, and similarly the second term in the denominator will also go to 0. It will become 1 by 1 unity, and your ET will be equal to EM, as would be anticipated, because both materials are having the same Young's modulus, so the mixture should also have the same Young's modulus, okay, whatever direction that might be. So that is essentially quite straightforward. But in reality, you know that ETF and EM will be different from each other. How much is that difference? A measure of that in a non-dimensional sense. The non-dimensionalization is done with respect to this particular sum, and that also involves a certain L by D factor in that. That is the length of the fiber to the diameter of the fiber, and this is going to affect. And in addition to beta depending on L by D, there's also a direct dependence, explicit dependence on L by D as well, and this can kind of affect your overall relationship. So this is one way in which it gets changed. The same thing is valid for the shear modulus as well, where you would have this particular relationship that is there, where you would include, instead of let's see, where is that coming in? Yeah. So typically you will not have this particular form factor for the GLTF and GM. So this is not bringing in any specific correction, so to speak, from L by D or the heterogeneity, but it is essentially doing it in a little more refined way by relaxing some of the assumptions that are typically made with the derivation of GLT. So that's why you don't see any betas or L by D factors in this, just that it's a little more complex relationship compared to the one we saw in the previous slide, which was based on the rule of mixtures. Now coming to the second example of a slightly refined micromechanics model, which is attributed to a researcher by the name Brintrop, is essentially because of the Poisson's effect. So the Poisson's effect can cause certain changes as far as the expression for ET is concerned, and that correction factor is coming through a quantity called EM prime, which depends on Vm squared. So for example, if Vm squared were approximately 0, so then you would see that the Em prime would be equal to Em, and you get back what you were what you saw in the previous slide. So that expression you get back, which is the reciprocal law. But it gets slightly corrected that instead of Em, you are going to use a slightly larger quantity, which is Em divided by 1 minus nu m squared, and this is kind of going to affect. So how these are derived? Many of them to some extent are derived based on experimental results. There are also certain thumb rules which are arrived at based on certain analytics and semi-analytics combined with certain experimental results. So in many cases these are not kind of actually rigorous physics derivations, or it is more of based on what is observed. You try to match that, so more like a curve fitting that you're trying to do, and you're trying to get empirical relationships. So it's a combination of analytical with the empirical relationship, what we call as a semi-analytical kind of a result that you see over here. Okay, so as I said, this is not something that you need to worry about from your course point of view. It's just to give you a flavor of what is actually done in reality, so that you don't go off thinking that once I know the rule of mixtures, I know all of micromechanics. Okay, so micromechanics modeling, based on the micromechanics modeling, now we are at a stage where we can actually look at the material performance indices that we derived earlier based on strength, stiffness and stability, which we called as sigma u by rho, square root of E by rho, and E by rho cube. So those quantities, all of which we were earlier comparing metals with fiber alone, but we said, and we saw last class, why fiber can't be used by itself. It has to be used along with the matrix. In conjunction with the matrix, the material properties come down. They're not as good as that it is for the fiber, but essentially you pick up certain properties in other directions where the fiber is weak, where the matrix contributes, and therefore now we are at a stage to compare oranges to oranges. So in other words, we can compare truly metal to composite, or between composites amongst themselves as well. So for these, as I said, when I say carbon epoxy, there could be many different carbon fibers that are possible, and different types of epoxy matrices as well. So depending on the grade of the matrix, the 5208 or 35016, each of these codes have a certain meaning in terms of how those epoxies are essentially manufactured, what kind of properties they have. These are based on the classification of different manufacturers of the fibers, and these are fairly commonly used fibers in the aerospace industry. So that's as far as carbon epoxy. Then there is boron aluminum, metal matrix composite, and then glass epoxy we use typically for low cost applications as a replacement for carbon epoxy. And then where the impact is a major issue or the dominant load, you use Kevlar kind of fibers, Kevlar 49 with epoxy, essentially an aramid fiber. So now we have the Young's moduli in GPa, the gigapascals, and the density over here in gram per centimeter cube. In SI units it would be kilogram per meter cube, where you multiply all of them by 1000 factor. And then of course you have the sigma u, which is the ultimate tensile strength now we are able to get our E by rho and sigma U by rho. Typically, if it's for dynamics, we will actually look at the square root of this, square root of E by rho. But if it's statics, then E by rho comparison is good enough. And there you see the differences between the various composites, and you see that the less expensive or cheap glass epoxy is giving you only 24 into 10 power. This is the unit for E by rho in SI 10 power 6 million meter squared per second squared, essentially because your Young's modulus is in Newton per meter squared, your density rho is in kilogram per meter cube. The Newton per meter square, the Newton can be written as a mass into acceleration, which is a kilogram into meter per second squared. You cancel out some of the meters, etc., and then you end up with just meter squared per second squared. Okay, and a common factor of 10 power 6 is pulled out to make this comparison a little more meaningful. And then you see the range of properties that are possible within carbon itself. Within the 3 carbons that are listed here, you could see a fairly good range of E by rho that is possible. And similarly over here, you see in terms of the sigma U by rho, the ultimate tensile strength by the density, which is a specific strength, and this is a specific stiffness, and that's a good comparison to have. This is more realistic, and this is what you really need to compare rather than the just the fiber, which is what we could do at that stage because we didn't have a micromechanics model in place, and therefore no way at arriving at E and sigma U for the composite as a whole. Now all that we described in the micromechanics in our limited exposure to that is deriving the moduli but not deriving the strength. That's an entirely new ball game. It's much more complicated to derive the strength of a composite as a function of the strength of the fiber and the strength of the matrix, even in the same directions that we discussed, because one failure typically happens before the other, and the kind of damage growth can also be multimodal. In other words, many different kinds of damages can be involved, starting from fiber breakage, fiber microbuckling, the matrix cracking, the fiber matrix debonding, delamination. So all kinds of things can occur, and they can occur in combinations as well, and therefore sigma U to get for a composite is very complicated purely from analytics. Mostly it is done using experimental results, and then there are certain cross verifications that are done with that. In fact, there are certain failure enveloped challenges that were thrown out by various journals and resulted in what is known as the WWFE, very similar to your WWF, which is a worldwide failure exercise, and blind data was given, partial data was given to many leading researchers around the world for each of them to come up with certain models for failure, and each of them came up with models, and many of them were disagreeing with the end results, and therefore they had to do a lot of corrections to it, essentially curve fitting, put in a more euphemistic way, politically correct way. So that's essentially what happened, and there were a series of these WWFE 1, WWFE 2 and 3, and each of them offered more and more refined models, and some of them do give very good results for certain specific cases, which is why we call them ad hoc theories or ad hoc models, but not for a general case, in which case you need to use combinations of those failure models by different people in order to achieve something which is reasonably good. So I think that kind of talks about that. So you would see that some will have low sigma U by rho, but very good value of the E by rho. So those are typically, as I said, used in cases where the dimensional tolerance is very strict, in that sense that you want it to be as less flexible as possible, in which case you end up with those kinds of materials. So all of these properties that we listed here are just the longitudinal properties, that is essentially the LL properties that we are talking about over here, whether it is the moduli or the specific moduli, or the tensile strength or the specific tensile strength or the specific tensile strength. All of them are in the LL direction, that is the longitudinal direction. It could be quite different when you get into the other kinds of directions like TT or LT, etc. LT, of course, would be your shear moduli, and then of course the Poisson's ratio would be also of interest. Any questions on this? So we continue to the last part of the homework for the next Monday, and this is 4.3, where remember we have already got these three material performance metrics or performance indices as we call it. So one is the strength for the strength based design, the stiffness based design, and the buckling based design, which was most sensitive to the mass and therefore to the density, and therefore the biggest advantage of composites is in these kinds of situations where compressive loads are involved, and we saw that compressive loads need not come explicitly as compressive loads. Even a shear load, etc., could in a different direction be a compressive load. So in many cases, even when there is no actual applied compressive load, there might be certain directions in which compression is important, therefore stability becomes critical in those places as well. And these are the units we typically use based on SI units for sigma, rho, E. When you substitute them, you will very easily see that they kind of reduce to meter squared per second squared, meter per second, and kilograms squared per meter per 8 divided by kilograms squared second squared. So the reason why I am listing this is we take out certain factors in order to compare different materials. We take out a factor of 1000 over here, a factor of 1000 over here, so that then we'll compare oranges with oranges. It becomes very easy. So and because this homework is based on a certain numerical data, I just want to put up front the units that I would like all of your results to be presented in, so that we have a good comparison, right? So what your exercise is going to be is in terms of identifying top 5 fibers. Remember, I started off the previous class with certain fibers from Torre, which were very high in modulus, very high in strength. I said that was the kind of state of the art 2 years back amongst commercially available fibers, but there are many other fibers, especially whiskers, etc., which can outperform them as well in terms of the Young's moduli along the fiber direction, as well as the strength, tensile strength along the fiber direction. So I want you to identify top 5 fibers each for each one of these designs. So that is for strength design, that is where sigma u by rho is the criteria amongst all the fibers that you can kind of lay your hands on for their properties. And one good source for getting material properties is matweb.com. So matweb.com lists a lot of properties for various materials, but there could be many other resources as well. You can, whatever resources you can lay your hands on, you can try to get to that. But you want to find top 5 fibers for strength design, top 5 fibers for stiffness design, top 5 fibers for the buckling design, which means that those specific parameters that we derive have to be maximized for those particular composites. Now, first of all, you are identifying fibers, but also we want to utilize what we studied in today's class, that is the simplest model of rule of mixtures for the composite, to get the composite properties in terms of the fiber and the matrix properties. In order to do this, we keep other things constant, so that essentially we are comparing the fibers, so that I want you to keep the composite, all of these composites. We'll go to one other part of the exercise. This is a polymer matrix composite, where the polymer matrix that is used is an epoxy, and a particular grade of epoxy which is having a, let's say the volume fraction is 0.4, 40% is matrix and 60% is fiber. So with maximum values for these 3 material performance indices, and as I said, focus on just these units so that we are comparing the right kind of things. Okay, the other thing is any chosen fiber, of course, should be compatible with the epoxy matrix. So don't just choose a fiber just because it is having very large sigma u. You should have some reason why it is compatible with the epoxy matrix. Typically that is given along with the fiber data. So make sure that it is compatible with epoxy, but most fibers are. So this is something that I'm just saying just to be doubly careful, but usually not an issue. Most fibers which are used in composites are typically compatible with epoxy matrix. As far as the matrix properties are concerned, again, epoxy can have a very wide range of properties. So let's not go around searching for the best epoxy and so on. I will just give you the epoxy properties which you can use, so that the only thing we are comparing therefore is with, in terms of the fiber properties which get into the composite. So, but these values are for the composite. Remember, sigma u by rho, square root of E by rho, and E by rho cube, I want you to compare for the composite after using those micromechanics equations that we already dealt with. And since all of these are in the longitudinal direction, just your EL will be good enough, and the same expression with E substituted by sigma u is good enough for calculating your sigma u. Density, of course, you know, given the density of two materials and their volume fractions, you know how to calculate the overall density. That also follows the exact same law that EL follows, right? So whether it is EL or sigma u or rho, they all follow the same rule, going from the components properties to the mixtures properties. So use Young's modulus for the matrix, that is epoxy, to be 3.4 gigapascals. Use its Poisson's ratio to be about 0.3, and then its mass density for the matrix to be 1200 kilogram per meter cube. But of course, for the fibers, you have to get those properties, because that is the challenge in terms of identifying the fibers and their properties, which include the Young's modulus, include the tensile strength and the density, in order to arrive at the composite values. Now that's as far as polymer matrix is concerned, but increasingly for high temperature applications we are going towards metal matrix composites. So therefore the second exercise will be to repeat the same exercise, but now with an aluminum matrix. Once again, checking the compatibility with the aluminum matrix is important. Not everything might go well with the aluminum matrix, so you have to identify maybe what you identified as the good choices for with the epoxy matrix. Many of them may not work with an aluminum matrix, so you might have to get an entirely new set of fibers, but there might be a few fibers which work with both, and that will be good enough as well. Right. So then for this again I'll give you the properties, because there are many different aluminum alloys which can be used as aluminum matrix, and therefore use Young's modulus of 71 GPa, VM of 0.3 and density of 2700 kilogram per meter cube. I think I missed out on the sigma u for either of them. So just assume a particular sigma u. Between the four of you, use the same sigma u for the epoxy and the same sigma u for the aluminum. Okay, so I think one data point I probably missed out on this. Yeah. So any questions? Yeah, Alexandra. Come again? Monday. And also cite all references. I liked Aryak, and I think Alexandra uploaded for the previous homework also. I saw that you had uploaded to Teams. So do the same thing for this exercise as well. Okay, so now we are, as I said, at the end of the last class, typical composite analysis is done in three parts. The micromechanics at the lowest length scale, the macromechanics at the structural component level, and in between a layer, a single layer, or what we call as a lamina, which is or even a ply for that matter, we typically call it. And how do you get the properties of that at different angles? So that's what we typically deal with as mesomechanics. We will not go into all the details of the mesomechanics results, because this is not going to be important. We have to soon get into how we analyze the macromechanics. That will be the rest of the course will entirely be about the macromechanics. So, but without micromechanics and mesomechanics, your macromechanics cannot even take off. So that's the reason why a briefing in these two classes, last class and today, about the micromechanics and mesomechanics was kind of essential. So which is what we are doing over here. So what are the assumptions that are involved in mesomechanics is what we would like to look at. And when we do this, this is something that is valid not only for any material models or structural models, but any mathematical modeling that you're going to do as part of not only this course, but any course that you take, or even as part of your career work in terms of modeling various systems. Whenever you talk about modeling a system, obviously you're trying to get into a mathematical model eventually, a set of equations which govern that which could be, let's say, algebraic equations, it could be differential equations, it could be integral equations, integro-differential equations, typically supported by boundary conditions and or initial conditions to get you to boundary value problems or initial value problems. But whatever they are, to lead you to that final boundary value problem or initial value problem, you need to make certain assumptions to get there. So it's not reality, it is a model for sure. But how close is that model to reality will depend on the kind of assumptions that you have made and their validity. Okay, so which is why whenever you do a modeling, whether it is composites or any other material or any structure, you are going to make certain assumptions, but you have to cross check, which is why I told you even in the homeworks, list them at the point they are invoked and argue out their validity. How valid are they? Okay, they might be valid for certain cases, they may not be valid for certain cases, so you have to give that warning as well whenever you give a derivation and present your final results. So first, two questions typically arise as far as assumptions are concerned. One is the necessity, the other is the relevance. So first of all, are all assumptions necessary? So each assumption one by one we go into at a point they are invoked and see, is it really necessary to go from step n to step n plus 1? Do I really need that assumption? Even without that assumption, can I go from step n to step n plus 1? So that's the kind of argument you try to make, and many a times you will find that, especially where even in some very good textbooks, they will list the assumptions up front and then they will do the derivation. Then you will see some of those assumptions are never used anywhere inside in that derivation. They might be useful for some other derivations. In other words, when certain assumptions are not even necessary, why make them? So you're thinking or making others think that your model is having lesser validity than it actually does, because you can probably do the same derivation without making one or a few of those assumptions. So that's the reason why it's important to invoke them where they are necessary, so that you know is it really being utilized or not. If it is being utilized and there's no better way of doing it, or it becomes too complicated if you don't use it, well and good, then go ahead and use it, but state it at that point, and so that becomes a part of your overall assumptions. The other thing is in terms of relevance, which is where you say, because you're going from reality to the model, yes, model is going to be approximate, but if the relevance is so poor, then it becomes a very, very poor approximation, may not be of much utility, purely an academic exercise that you're doing, and really not worth it. So it's also important to check whether each of those assumptions are relevant or not, okay, for that particular material or that particular geometry, etc., when you're talking of structures or material modeling. But same thing holds whatever you're modeling, whichever kind of system in any course. Okay, so now let's get going with the assumptions that we are going to make as far as this course is concerned. For the entire structural analysis, whatever we are going to do in the remaining 11 classes, all of them pretty much will make these assumptions. Some of them may be invoked, some of them may not be invoked, but at least a subset of these will be utilized in all the theory that we develop, as well as the homeworks that you're going to be solving. You will see a certain subset of these assumptions being made. And I will use a color code over here. I will use green to say that these are passing these two tests that I talked about in terms of necessity and relevance. Yes, these assumptions are necessary, and they are also relevant for a lot of things that we are going to do. So what is it? The first assumption that we are making is that whatever structural analysis we are going to do is going to be of a structure of a certain geometry, but also going to involve certain materials. So we make certain assumptions regarding the material. One assumption we make regarding the material is that it is elastic. What does it mean? What does elastic material mean? Anybody? When you say a material is elastic, the other option is it is inelastic. It's not elastic. So when you say it's elastic, what does it mean?
Is it that like after it gets like the alternate like tensile strength, it's able to go back and revert to the same shape?
The second part is right, but it's not necessary that you go all the way up to ultimate tensile strength, because most materials, once you go there, it's already failed, or even when you go much below that, already it's beyond the elastic limit. So, but essentially for lower values of stresses and strains, essentially your loading and unloading paths are one and the same, right? So, anybody else would like to define an elastic material from what you know? It's what? Non-deformable, okay. Non-deformable, we say it is essentially a rigid body, right? So it's not undergoing any change in shape or size, okay? So that is a very, very special case of an elastic material with the modulus of elasticity being infinite, okay? So yes, that is a special case, but that's not something which is interesting for us in this particular course. It was very interesting in, let's say, a course like AE2020, which is essentially dynamics of rigid bodies and or particles. So there it could be useful, okay? But what you're saying is absolutely right, that that is a special case of an elastic material. But our elastic materials which you're going to use for structures are much, much more wider, and most of them will have a finite Young's modulus, not infinite like a rigid body, but it will be a constant. So in other words, essentially what you're saying is that you're looking at this elastic material means that you're, as Nilesh pointed out, it will be having the same loading and unloading curve. So in other words, if I plot sigma versus gamma in a particular direction, that will be a single curve. And what does a single curve mean in terms of mathematics is that it's a unique functions. In other words, it cannot have multiple values. So let's see what all of this means in terms of a graphical representation. So remember that there are many different stress components, many different strain components. So we take a particular stress component, we'll say sigma ij, and some strain component gamma KL. Okay, so typically we plot this for sigma 11 versus gamma 11. It just becomes along the along a particular direction. You are applying a normal stress and measuring the normal strain, let's say using a strain gauge in that parallel to that direction. Then you tend to get material points. So you start getting, as you conduct the load, you will know what is the load. This is typically done in a UTM, universal testing machine, where you have a certain, based on certain ASTM standards, you design a particular specimen, you start applying a tensile load, you know how much load you are applying, divided by the cross-sectional area at the test section, you will have the stress, uniform stress, and therefore that stress gives me the y coordinate on this, and then I have strain gauges which are parallel to the specimen, so which are attached to it, and that will read the strain levels. So I have, for each stress I have a particular strain, so I start collecting all these points that I read out from my data, right? So when I try to join them, typically at least in the initial portion it will be a straight line, but whether it is straight or not is not something as part of elastic material. Elastic material, all that it is saying is that there is only one curve which connects these. In other words, whether I am increasing the load or decreasing the load, it will always be going up and down this particular curve. Okay, so that's essentially what we are talking about. So whether I am starting from a zero load and going to a large load, which is the direction of the arrow over here, or I am coming back by, after going to a large load, I am reducing the load and coming back to zero load. In either case, I will be retracing the same curve. I will be getting more points on this curve if I am reading it at different points, but essentially all of them are on the same curve. And I am repeatedly saying curve and not a line, because this is, it could for another material be something like this, right? And if it is elastic all the way up to this, all it means is that it goes up there and comes back there, right? So this is for material 1 and material 2. Now both these materials are elastic materials. So this is also elastic. This is also elastic. The reason is, as long as I'm not increasing the stress and strain too much, I am always able to come back on the same path, and eventually when I remove all of the load, all of the strain becomes zero. There is no remnant stress or strain which is remaining, which is a residual strain. There's no residual strain. Residual strain is zero, in other words, right? So that is essentially what we are talking about. So what does it mean in terms of mathematics is that I have a sigma ij as a function of my gamma kl, and this is a unique function. So in other words, if I fix my number for gamma kl, I get my sigma ij fixed. So there is no way I can have two, or a material is not elastic. For example, it could have had something like this. In other words, the curve for loading and unloading could be different, and therefore it is possible for a given value of gamma I could have two different stresses, or for a given value of sigma ij I can have two values of gamma kl. Okay, and when I say ij and kl, I am fixing ij and kl as specific values, anything between 1 to 3. Okay, so this could be, for example, gamma sigma 2 3, then I am plotting it versus any particular gamma. It could be, let's say, gamma 1 3. Okay, but what is of most interest to us is the like kind of materials, because that populates the diagonals, or if it is having a matrix kind of a representation, then we are looking at the diagonal terms, principal diagonal terms, and therefore that's of interest. But this is something that is valid for all ij and kl, even when ij is not equal to kl. Okay, so that is essentially what we are talking. That is the very first assumption that we are making. We are saying that is elastic. One way of looking at it physically is that the loading and unloading curves are one and the same when you perform a test. But what is it mathematically? It is saying that sigma ij is some function of gamma kl. This need not be a linear function. This could be a non-linear function, which is why I'm just saying sigma ij of gamma kl. And all of the gamma kls can be involved over here. Remember, ij, kl, all of these take on the three spatial coordinate directions, and therefore they can have the values anything between 1, 2 and 3, each of them. Okay, so IJKL can take on any values between 1, 2, 3, and they can be repeating as well, doesn't matter. But essentially you have the number of strains that are there, because there are 3 choices for K and 3 choices for your L. They are going to be total of 9 quantities within this bracket. In other words, a single particular stress component depends on any one of those 9 components over there. Similarly, you have I can take on 3 values, 1, 2 and 3, and J can take on 3. This also 9 different components, 9 different stress components, 9 different strain components. They're all in general functions of each other, all of the entire set. I can write the reverse of this function, the inverse of this particular function. I can put my gamma KL as a function gamma KL, a nonlinear function at that, of my sigma ij's. Okay, once again I have 9 such equations where each of those 9 quantities depend on the 9 stresses, and therefore I have the set. So of course the most direct dependence will be when I fix a particular KL and fix the same values for I and J respectively. Then it's a direct relationship, but there can be other relationships like the Poisson's ratio effect, for example, that we already saw. So something like that can cause off diagonal elements as well, but this is essentially the picture. So what elastic means is that these functions are unique valued functions. In other words, given a set of sigma KL numerical values, there's only one sigma ij for that particular material. There cannot be 2 different sigma ij's. In other words, loading and unloading curves are one and the same, is equivalent of saying that in a mathematical sense. These functions that I have here on the right hand side, whether it's the direct or the inverse, both of them are essentially single valued functions. Okay, so that's as far as elastic material is concerned. And as I said, based on our color coding, it's in green, which means that most materials that we use in aerospace structures, be they metals or composites, are mostly elastic, at least until they fail or very close to their failure. And most of the time we are analyzing healthy structures, and therefore elastic model is a reasonable model to continue with, and this is something that we will use throughout the course. Okay, there's a second thing that we make. The second thing is about linearity, and linearity has its own different nuances. One is geometric non-linearity, which we will come to a little later, but right now we are talking about so-called material linearity. What does material linearity mean? From this point of view, that structural analysis, when we say a material is a linear material, what do we mean?
Would it mean that like the modules would be like linearly elastic? No?
Yeah, so these are two different things, elastic and linear. So it could be elastic and linear, or elastic and non-linear, or not inelastic and linear, inelastic non-linear. So let's be a little careful about that. But you're heading towards the right direction. Just modify what you said a little bit. When do you say a function is linear? A particular function is a linear function of something, some other variable. Say, let's say y is a linear function of x. What does it mean?
Means like the slope is just constant.
Good. Yeah, slope is constant. In other words, the line is a straight line when you plot y versus x. Yeah.
So does it mean that it follows Hooke's law?
Exactly. Right. So Hooke's law in its simplest form is essentially involving constants. So you're essentially saying that the functions that we wrote over here, sigma ij is sigma ij of gamma kl. This could be any function. It could involve gamma squared, gamma cubes, sine of gamma, cosine of gamma, logarithm of gamma, exponential gamma, whatever, right? It could be any general function. But now we are restricting, as you said, to linear functions. In other words, there's a really linear relationship between sigma ij and gamma kl, of which Hooke's law is a very special case, where we are saying that for example, sigma 11 is equal to E times gamma 11, where the constant of proportionality between sigma 11 and gamma 11 is E under certain conditions, which we will not state right now, but under certain conditions that is valid. But what this means in a more large scale is that a generalized form of Hooke's law, as you said, and a generalized form of a straight line that you said. So here, remember, we drew two examples of elastic materials. Both were elastic, but only one of them is a linear elastic material. Which one is the linear elastic material? The top one or the bottom one? Top one, because it's a straight line. Okay, so it involves a straight line. So therefore, you can express this functionality form as a linear function, and therefore you see that that is a linear material. Okay, so keep in mind, though we are kind of adding up the assumptions one after the other, each of them can be taken independently. So in other words, as I said, you can have a linear inelastic or a non-linear elastic or non-linear inelastic, etc. All kinds of combinations are possible, because we are talking of two different aspects over here. What is the aspect we are talking of? One, we are talking of saying that it's a unique valued function. That unique valued function can be a linear function or a non-linear function. The other one, what we are saying, it's a straight line, but that straight line can be one straight line or multiple straight lines, in which case you can have a non-unique function, in which case it is inelastic. So it is very much possible. So for example, a classic case where you could have let's say something like this is an elastic, it's a linear material, because there are straight lines, but at any given stress I have two possibilities for strain, or at any given strain I have two possibilities for the stress. So therefore it is not a unique function. So therefore it's not elastic. So this is an example of an inelastic linear material. Okay. Whereas this is an example of a linear elastic material. So it is elastic and linear, right? whereas this is an example of an elastic and non-linear material. Okay, most general case being an inelastic non-linear material where you have curves for both going up and down. So essentially you could have like what we showed already over here. If this was the curve going up and going down, so essentially you have non-unique function over here, and therefore you would have an inelastic non-linear model, right? So the reason why I'm showing not in green but in yellow is that yes, material linearity is valid up to a certain level of strains, but many cases you might be using the material beyond that, even in the actual operation, regular operation, not like an emergency accident situation or impact situation, but even in the normal operation of an aircraft or many flight vehicles, you might be extending the strain, because the whole idea is that we want to get as much as we want from these materials and geometries, because weight is at premium for us. So we would like see we have such a limited amount of weight that we can use for structures that we let the material go into the non-linear regime. It's not failing, it's just getting into the non-linear regime, so we can still handle that. It's just that for example some different metals behave differently, but it can be linear up to a particular, is a good approximation, but there can also be a small non-linear regime over there, but it might still be elastic in the sense that it is going to trace back. Up to this point, I would say the elastic limit, which is linear. So this is a linear elastic limit, and now this is a non-linear elastic limit. In other words, both are elastic in the sense that they are going to trace back the same curve. How many ever times you're going up and down on that, that doesn't matter, but it's just that part of it is straight line, a part of it is curved, which is having a essentially a non-zero curvature or a non-infinite radius of curvature, and therefore it's essentially non-linear, right? So that possibility is there, and therefore we put it in yellow, that most of the time it is valid. Just like your traffic lights, you have red, yellow and green, right? So green is like always to go, and if it's amber or orange or yellow, they typically see that you have to wait and watch, right? So it's like somewhere in between. So most of the time it is valid, but just that you have to be a little careful, cautious about employing that assumption, okay? But as far as this course is concerned, we will throughout assume the material is linear. Now this is an assumption which most textbooks will not even state. They will take it for granted, they will and still be utilizing it actually implicitly, and this is what leads to a lot of simplification in terms of our model, and therefore it's a very, very important thing, and this is a valid assumption. So there's nothing wrong in making that for most materials, unless you have this is a kind of a giveaway for a question that I'm going to ask later, but I'll still give it away. Unless you're using magnetic materials, then this assumption is not valid, and therefore you would have an issue with making this, and there are certain simplicity that we will take forward in the rest of the course, which will not be valid in such kinds of materials. So what is this body moment? Have you heard of body forces? Yeah, what can you give me an example of a body force? Good, yeah. So weight is a example of body force, which is caused by gravity, as you said. So essentially, why do we call it a body force? What is so special about that force which needs to be qualified as a body force, as opposed to some other kind of forces? Yeah. So suppose I have this and I'm trying to push this. This is also acting on the body of this, right? So, but this is not a body force, right? But the weight is a body force. So, can you think a little more why it's called a body force? Weight is a body force, but this push, or let's say I pull, those are not body forces.
Does it have to do with like the mass of the material?
Correct? Yeah, a little more. It need not always be about the mass, but it's something to do with the material. Yeah. So what exactly is happening? So by body we mean their entire body, right? It's not just the surface, or we don't call our only our skin as the body, it's the entire body, right? So when you say gravitation or weight is a body force, essentially it means that every, yeah, you are about to say something? Yeah. Okay, so every point or every particle that constitutes the body is experiencing that force, and it's the overall sum of all those forces that each particle of the body is experiencing that the overall body is experiencing, right? So in other words, it's a distributed force. It's a force that is distributed not just on the surface of the material, but throughout the interior of the material as well. There are material points of this object inside which are also experiencing that weight, okay, because each of them has a certain density, and based on their volumes they are having a small dm mass, and therefore a dw weight, which is multiplication of dm with the gravity acceleration due to gravity g, 9.81 meter per second squared. So essentially it's a distributed force that is there at each point within the body, large or small, depends on the specific material that is there. It could be made out of multiple materials, some having low density, high density, just like in the fiber matrix composite, for example. The fiber will have entirely different density, material density from the matrix, and so it could have different weights for the same volume, right? So, but essentially there is a non-zero contribution at every material point, large or small. It is essentially a distributed force within the entire body, and that's why we call it a body force. So what about a body moment then?
So I'm guessing like the movement is it like so for body movement it'd be like it's a movement that's distributed throughout like the entire body.
Absolutely.
All the compartments in it.
Right. So it's just extension of the body force definition, that this is a moment which is distributed throughout the body. Every particle that you take is experiencing a certain couple or a torque, a moment which is essentially trying to rotate it, right? So a point's rotation doesn't mean much, but essentially when you're taking an infinitesimal volume, which is not zero but essentially a finite volume, but making it smaller and smaller, then it can actually be rotated in different directions, and what can rotate it is a moment. Just like what can move something is a force, what can rotate something is essentially a moment, right? So that moment, if it is acting at all points within the body and it's kind of distributed, and the overall effect of that can be integrated throughout the volume of the body, then we call it a body moment, okay? And one example of it is what I already gave you, which is the magnetic material, which typically has dipole moments, dipoles distributed throughout, and therefore they can be, if it's in a magnetic field, then it can experience moments at all points wherever it is, because there's within each block of small material, infinitesimal material that I take, volume, there is going to be a pole to it, a north pole and a south pole to it, is essentially a dipole, and there can be within a magnetic field experience of certain moments that are there. But rarely we use magnetic materials to make let's say a structure, whether it's the spar or the skin of a wing or whatever. You rarely use a magnetized material. You can use steel or iron based materials, but essentially they are not magnetized, right? So it's essentially used in a form that is not magnetized, and therefore it's the presence of dipole moments is not of a concern over there. So that is only one example. There could be many other examples where such distributed body moments can be there. So what is the issue if body moments were there? So this is an assumption that we are going to make. The fact that I have made it in green means that it is kind of necessary to simplify a lot of things, otherwise we're going to have a big headache. I'll tell you what that headache is, but it's also relevant, okay? So what does this mean, that when you have no body moment, what is the simplification that you kind of anticipate? Remember that we are starting our journey with this particular equation. So either you can tell it in a mathematical form or you can tell it in a physical form. Both have their validity. In a mathematical form, what have we been doing? When we didn't have anything, we said that there are two quantities, sigma and gamma. We had no idea how to relate it. But once we said it is elastic, we said that yes, there is going to be a unique functionality between the two. I can write sigma ij function sigma ij of gamma kl, or I can write it inversely as gamma kl as a function gamma kl of sigma ij, two nonlinear functions I have, right? Though it's two sets, because each of them will have nine functions, nine direct functions, nine inverse functions, 3 into 3, because I and j take on 3 values. Similarly, k and l take on 3 values. Okay, so that's what the first assumption told me. The second assumption told me, yes, this is a linear material, so that I can express this as a linear function. One is in terms of graphical, that means it's going to involve only straight lines, not curves, and which in a mathematical term, that second assumption, even before we get into the third, should have meant, I should have written it here. So once you have that, so this equal is valid when I say the first assumption that I made there, that I said it is elastic. Okay, now I will say one more thing over here, and this equal to will be valid when I have material linearity. So once I have material linearity, I will have this equal to possible. What is that equal to? I can write this as a Cij KL into a gamma KL, and this I can write as some Sij KL times a sigma ij, where C and S are constants, and there are 3 into 3 into 3 into 3, that is 9 into 9, 81 C's and 81 S's that are there over here, right? So these 81 quantities are all constants. Only then I can have a linear relationship between my sigma ij and gamma kl, or the inverse relation of gamma kl of sigma ij. So in other words, they are all constant, which is what Ariek pointed out, that Hooke's law is valid. So Hooke's law is just relating one stress to one strain. Here we are relating one stress to all the strains, or one strain to all the stresses, right? So and each one of them is a constant. Okay, the constant that you refer to is specifically when I fix a KL as say 1 1, I fix this also as 1 1, so then I'm talking of an S1 1 1 1, right, which is having a 1 by E form, or a C1 1 1 1, which is having a E form, which is a Young's modulus form, right? Now keeping all the other things 0, so that that kind of validity is there, right? So now you see that one by one, as we are making the assumptions and adding those assumptions, I said that they can be independent. As I said, they can be combinations, right? Elastic linear, elastic non-linear, inelastic linear, inelastic non-linear. But if I make both of those assumptions together, as I make elastic assumption and material linear assumption, then I end up with this simplification that I have, right? Now what kind of simplification that third assumption can make when I have no body moment? What does it do for me? What is the advantage I get? In terms of this equation, how can I further probably simplify that? In when you studied deformable bodies, though I know it's a little while ago, saw that sigma ii is a normal stress, right? If you have sigma ij where I not equal to j, then what kind of stress is that? Yeah. This is a normal stress. If it's positive, it is tensile. If it is negative, it is compressive, right? What about sigma ij if I not equal to j? Yeah. So another name for that? Transverse. Good. Another? So remember, yeah. I think you mentioned it, but essentially you're talking of two subscripts here. One subscript stands for the area or plane on which it acts. The other is the direction in which it acts. Essentially, it's a measure of a force per unit area, whether it is this or this. It's a measure of a force per unit area, and so if you're talking of a cuboidal structure like this, essentially what you're talking about, let's say you have x, y and z coming out of this. So let's say you have a model like this. So then what you're talking about is that if you the first index refers to the planes. For example, the first index is x or 1 because this is equivalent to saying x1, x2 and x3 as well. So if I say 1, 1, it means that it's on the one phase. That means it is perpendicular to the x1 axis and the force is acting in the x1 direction. So in other words, I apply a force F1 on a plane to which the normal, the unit normal is I hat, which is along the x1 direction, right? So it's the unit vector, right? So in other words, because it is in the x1 direction plane with the force F1, so therefore that divided by that area is essentially what I mean by sigma 1, 1. On the other hand, this phase is perpendicular to the z axis or the 3 axis, and therefore any stress which is acting on this phase will have the first subscript as 3, and if it's a normal it will be 3, 3. It will be a 3, 1 if it's a shear stress, as Aryak was trying to whisper, a 3, 1 or a 3, 2, right? So essentially these are called as shear stresses. This is on the 3 phase because of z or x3, and it's acting in the x1 direction, so it's a 3, 1. So similarly, if I have a stress like this, it is a sigma 3, 2, right? So on the other hand, if I have on the top surface over here, I would have a stress which is coming like this, which is sigma on the 2 phase. So the first subscript will be 2 because the normals are with respect to y or the x2 direction, and it is acting in the z direction, and therefore it will be 2, 3, right? So you have a sigma 2, 3. So similarly, you would have a stress like this, which is your sigma 1, 3, right? So now you see that there are all these quantities which are having different subscripts, that is the same number is not repeated. Then these are all, as you pointed out, tangential or which is parallel to the surface. We are essentially rubbing through the surface either in this direction or this direction. So that is essentially what, as Arya pointed out, shear stress. Okay, so this is a shear stress as opposed to a normal stress that you are having, which could be either tensile, which means it's positive, or it could be compressive. Okay, how do you have a positive negative convention for these shear stresses? Positive negative for the normal stresses are that tensile is positive, compression is negative. So it's quite straightforward. What about for ij when I and j are not equal to each other? For example, your sigma 3, 1, the way I have shown, is it positive or negative? You don't recollect? So essentially the way we decide the sign for it is that we see what is the normal direction to it. Is it along positive z or negative z? So here it is positive z, so 3 is the normal to that plane is positive, and if the direction of the force F1 is along the this should be F2. So this is sigma 3, 1, this is sigma 3, 2. So it's along the positive 2 direction. So it's on a positive phase in the positive direction, then it is positive. If it's on the negative phase in the negative direction, then also it's positive. Only if these two are interchanged, that's on the positive phase, if it is in the negative direction, then it's a negative stress. Or on the negative phase, if it's in a positive direction, then it is a negative. So if they are kind of inverted, these two, that one of them is positive, the other is negative, then you take the stress as negative, otherwise you take it as positive, right? So that is as far as the sign convention is concerned. Now getting back to this third assumption, the place where it kind of simplifies for us is in terms of one of these shear stress expressions. Do you know anything about the relationship between let's say a sigma 2,3 and a sigma 3,2? So remember, by definition, sigma 2,3 is acting on a plane to which x2 is normal, or in other words, the j hat vector is normal in the k hat direction, because of the third direction along the x3 or z direction. So this is what it is. Whereas here it's acting on the 3 plane, that means a plane to which x3, k or z is normal and z axis normal, and it's having a force which is acting in the x2 direction, right? So now, are these two independent quantities? If they are not, how are they related? Is there anything that you remember?
So for like a no body movement, like those two things like opposite?
They will be equal, not opposite, because they are on different planes, remember? So for example, if you take sigma 3,2, it's acting on this plane, and sigma 2,3 is acting like this, okay? So they're not opposite to each other, they're at right angles to each other, right? But what you're saying is right, that their magnitudes will be equal to each other. So in other words, these are equal to each other, and this is actually valid if and only if there is no body moment distribution. Nobody will tell you this. At least I have not seen anywhere, any textbook or anything which kind of mentions that under this condition this is valid. They will derive it almost as if this is always valid, okay? But this is an important assumption. That's why I'm trying to tell you at each point of invocation of assumption, at each step when you move from one step to another, n to n plus 1, try to think of all the assumptions that are either kind of explicit or even kind of implicit. It's important to bring it out explicitly so that you are very clear about both the necessity as well as the relevance. That way you are always clear about when your mathematical model is valid and when it is not, which is very, very important, because you don't end up applying an invalid model somewhere, or you still have a valid model but you think it's not valid and you are sitting how to solve this problem. I know the model, I know the problem, I know I can put this here, but because of an assumption that I think I have made, therefore I'm not applying, saying that it's not valid for this problem, but actually it is valid for this particular problem. So that's important to kind of understand and bring in both of these aspects of necessity and relevance to each and every one of your assumption, and this is one such thing. For example, you might be dealing with some place where there is a magnetic material and it's in a magnetic field, and you start using this because this is kind of used even in your sleep in terms of sigma ij equal to sigma ji, always you tend to use, and then you might get very wrong results because the body moments might be putting that for a toss. So just like body forces like gravity are per unit volume or per unit mass, similarly you have these body moments also per unit volume or per unit mass. You can define it as densities of these distributions, and that will kind of come into picture in terms of making the difference between these two if it were to be present. But most structural materials, as I told you already, do not have body moments, and therefore this is something that we kind of take for granted. And this is one example, but in general you can say sigma ij equal to sigma ji, and I don't even need to say I not equal to j, because even when I equal to j, this is still valid because I would still be I on the right hand side as well. So let me stop with this 3 assumptions. We'll continue with a few more assumptions that we'll make. Some a little more dicey, some in yellow, and some will be towards the end will be in red, showing that they are really not valid for most aerospace structures, and still a lot of people make it, but we can do without that, which is what most of our course will be focused on. How, if those assumptions are still not valid, we can still utilize it, because that's the reality.